All right, so let's talk about the alpha and beta forms of these saccharides and why we have to make this designation between alpha and gamma. So up here I've drawn the board a simple aldose, and for simplicity let's put all the alcohols on one side. And the question is, what happens when this alcohol attaches this to this ketone group to give you the acetyl? Well, what's going to happen, and hopefully you can see it here in the video, is that we have our alcohol on the very end of the chain. So there's our ketone, and then we've got the different backbone alcohols. And ultimately finish it with this alcohol, and the alcohol can attack in two places. It can attack either on the bottom, or it can attack on the top. So depending on where it attacks will dictate whether or not this ketone ends up or down relative to the other alcohols. So we need to designate which one is which. And for me, this part's a little confusing. I don't understand why you would draw the Hayworth diagram this way, but this is the way they're going to draw it. So to figure out if we have the alpha or beta form, what we're going to do is, well, first of all, we need to figure out how big the chain is going to be. If we can form a 6-membered ring, we will form a 6-member ring. If we only have the option of doing a 5-member ring, we will form a 5-member ring, but we're going to start counting down. So 1, 2, 3, 4, 5. So we can form a 6-membered ring. Remember, when we form these Puranos rings, we do so using one of the alcohol oxygens, the carbon backbone, and we're going to attach that 6-carbon to the carbon attached to the aldehyde or the ketone. So to figure out which form we have, we're going to use a Hayworth projection. And in this Hayworth projection, we're going to do two very important things to keep us consistent. First of all, this oxygen here is going to form one corner of our 6-membered ring. The second is that this aldehyde carbon, this carbonyl carbon, is going to form this carbon position here. So we have 1, 2, 3, 4, 5, and 6, corresponding to our 6 positions here. 1, 2, 3, 4, 5, 6. Now, in laying it out this way, and you may need to use the modeling kit for this, we're going to end up putting all the oxygens. So this is, this is basically the Hayworth projection in 3D. We're going to end up putting all the oxygens down. So you're probably going to have to build your modeling kit to do this. But the alcohols on the 2nd, 3rd, 4th, and 5th carbons are all down. Hydrogen's up. Now, when this oxygen attacks, it can attack from either side of the ketone. So as I've got it built here, we've got our ketone trigonal planar, and the alcohol can either go from the bottom or from the top. Now, if it goes from the bottom, what it's going to do is it's going to push our carbonyl oxygen down, or our ketone aldehyde oxygen down, and the alcohol is going to go down. Or if it attacks on the other side, it can push it up. If the OH group is down, this is the alpha form of the Puranos. If the alcohol that we generate by reaction of our terminal alcohol with this aldehyde goes up, this is going to be the beta form. And this is going to be true for the ketoses as well. So for aldoses, it's easy to see because you're basically going to convert this aldehyde oxygen into an alcohol. If it's down, it's alpha. If it's up, it's beta. Even if we have a branch coming off here, so let's say we have a CH3 for the ketose group, we're not going to care about what happens to that ketose group. But we're not going to care what happens on the other side of the carbonyl oxygen. Again, if the alcohol is down that we generate from the ketone oxygen for the ketosis, we're in the alpha form, and if it goes up, it's the beta form. So this is how we discuss how it interacted. Now, a thing to note about this is a reversible reaction, and we can actually isolate them. We can cool them down and travel them in different forms, so we can definitely isolate the alpha and beta form. But keep in mind, these are not fixed things. So like things like cis-trans, there's like complicated reactions to make them go switch between cis and trans. This is an accessible reaction that can be done at room temperature, but to the same extent, it's stable enough that we can actually isolate these two forms, which is why we need to designate which the forms we're working with.